In this video, I'm going to talk about PT-symmetric mapping of three states and its implementation on a cloud quantum processor. So this presentation is based on this publication, which is accepted to Quantum Journal. So what our PT transformation is doing is taking three arbitrary states on the Bloch sphere and transforming them into another completely arbitrary three states on a Bloch sphere. So this transformation succeeds with certain probability of success, which like you can find more details in our paper. And essentially it is similar to as if you have a globe, and on that globe you have three cities. So this transformation essentially maps arbitrary three cities on the globe into another three arbitrary cities on the globe. And here are partial cases of this transformation. So in this case, two of the states, like first and third, coalesce, so they become the same, like they essentially merge. And in this case, another two states essentially merge. So these two cases are actually most relevant for practical applications. Nevertheless, you can transform this to arbitrary set of states, for example, to mirror symmetric ones like this. Um, and now you can ask me, why should we use this PT-symmetric transformation in the first place? Well, because this gives you advantages in like practical applications. Namely, it gives you reduced readout cost in depth-limited Grover search. So essentially, when you have depth-limited Grover search, then you would need to, so punctuated version of Grover search. Then you actually, when you attach Anzilla and perform such transformation, you would need to read and work in qubits only once. And in the end of depth-limited Grover search, you are skipping all these readouts when Anzilla clicks 1. So because in this case you will know for certain that this corresponds to failed results, so when there is no solution. So let's say if you have so basically, if you have a Grover search which is depth limited, essentially you need to read and work in qubits only once for arbitrary depths of that circuit. That would cost more, more oracles, but you would need all qubits only once. Then also, it gives advantage in higher information to cost rate for quantum sensors. When the cost of measurement is very high, then information to cost rate achieved by PT-symmetric sensors is much higher than that of Hermitian ones. However, what we found using our explicit expressions for this transformation is that this condition can be drastically relaxed, and in fact, even under modest experimental conditions in much wider range of in just much wider range of parameters, PT-symmetric sensors beat their Hermitian counterparts in terms of information cost rate. So you can see this. It is important to note that our algorithm is already implemented as an optical scheme by other researchers in this paper, and you can see that our preprint is cited there. And basically such solution can serve as universal solution for discrimination of arbitrary non-orthogonal quantum states, as discussed in this paper, because essentially you can transform arbitrary three states to a standardized set of states. And actually, even so, as you will see, even when post-selection fails, this still gives you some knowledge about the states under post-selection, because like different states have different success probability. Okay, so and also, as it is noted in this paper, that cost of such discrimination is a dissipation of quantum states into the environment, which actually corresponds to the fact that such such transformation is actually um, probabilistic quantum gate. So essentially, sometimes it works, sometimes it doesn't. Sometimes it works, sometimes it fails. And in this paper, success probability was not found. So since then, we greatly extended this paper, and plus we implemented this on IBM quantum experience. So here is the table of contents. So that was like high level overview, and now there is a table of contents in digging in more detail. So first I will describe some background on PT-symmetry, some necessary background that you need to know. Then I will describe our algorithm for extended PT-symmetric quantum state discrimination for 3 states. Then I will describe exact expressions for probabilities of successful pulse selection for 2 and 3 states. Um, and unlike previous work, we found these exact expressions, because in previous work, other researchers implemented this by numerical computations. And in our paper, we did both. We both implemented numerically, and we found exact expressions for maximum probabilities of successful pulse selections analytically. After that, I show the implementation on IBM quantum experience. As an example, I will show an attack on 3-state QKD protocol using our scheme, and then we'll describe technical advantages of our scheme, namely information cost rate for quantum sensing and PT-symmetric Grover search, which achieves the same success rate in terms of number of oracles, but at lower qubit readout cost. Finally, I will discuss the conclusions and outline future work. So all this like research on PT-symmetry started from the eigenvalue problem. Like, for example, if you have oscillator Hamiltonian, which is p squared plus x squared, it was found that some like crazy Hamiltonians, such as p squared plus ix cubed, have real eigenvalues, which was a really big surprise at that time. And it is important because energy values should be real, like complex eigenvalues that correspond to the case when probability is leaking, for example, radioactive decays. Nevertheless, the sum of probabilities must be 1, because particles don't disappear, they just decay to some other particles, and thus fundamental description must be in terms of real eigenvalues. And then it was shown that actually those type of Hamiltonians belong to a more general type of PT-symmetric Hamiltonians, and if PT-symmetry is unbroken, then all eigenvalues are real. So basically, a parity operator is just mirror symmetry flip. Time reversal is complex conjugation. Hamiltonian is called PT-symmetric if under this transformation it becomes itself. So, for example, this Hamiltonian is PT-symmetric, because if you just flip p to negative p squared, and then if you flip x to negative x cubed, but also complex conjugate, then this is 1. So this becomes itself. And PT-symmetry is said to be unbroken if all eigenvalues of these Hamiltonians are also, if all eigenfunctions of these Hamiltonians are also eigenfunctions of PT operator. And if PT symmetry is unbroken, then all eigenvalues are real. So this was rigorously proven in the 3 papers, and therefore PT-symmetric quantum mechanics is a self-consistent theory. So here is a simple illustration by Katarina Zarudna. So the girl on the left is getting younger, so the clock for her runs backwards, while a mirror symmetric girl on the right is getting older. So these girls have clocks running in opposite directions, but they are also mirror symmetric, and thus they are PT symmetric, right? So at this point you may ask, does PT symmetry give any new effects in comparison to Hermitian case, especially given the fact that arbitrary PT symmetric Hamiltonian can be mapped to Hermitian Hamiltonian by such a transformation? So this type of transformation was discussed in many papers. Originally, I think it was proposed in the paper by Mostafa Zadeh, You can find a complete list of references in our paper because there is lots. There are many papers on this transformation. But thing is, you can always map PT-symmetric Hamiltonian to Hermitian ones by such a transformation. And the problem is that yeah, and thus you might think that whether PT-symmetric actually gives any new effects in comparison to Hermitian case, and the answer is yes, because uh, this map is non-unitary, and orthogonal eigenvectors in one representation may become non-orthogonal in the other, and PT theory actually includes extra symmetries. So in this case, this is represented by charge conjugation operator, which is basically sum of eigenfunctions. And yeah, so you can find explicit formula in the relevant papers. And for the case of qubit, it gives an extra parameter that enables faster than Hermitian quantum evolution, uh, like uh, like was theoretically predicted in this paper and experimentally observed in this paper. So actually, this is the graph from this paper, and actually you can see that evolution time in PT-symmetric system is faster than in Hermitian one. This doesn't mean that so time is smaller not because evolution is actually not because the speed is faster, but because the distance is smaller. So this alpha parameter enables to control the angle between the vectors, and basically, if you in such a case you can like in PT-symmetric case, the vector has to turn on smaller angle, and as a result, evolution is faster. Yeah, in fact, we are using this alpha parameter in our paper as well. So yeah, but we use this alpha parameter to manipulate the angle between the states. So for the case of qubit, general Hermitian Hamiltonian for the case of qubit is given by this in the most general case, because if you complex conjugate and transpose, it becomes itself. But for the case of PT-symmetric Hamiltonian, it is given slightly differently. So PT-symmetric Hamiltonian, because PT-symmetry, it's a condition. So hermiticity is a condition only on the Hamiltonian. So basically, if Hamiltonian is Hermitian, then eigenvalues are real. But PT-symmetry is a condition on both Hamiltonian and also eigenfunctions. So if you take a look at this, you can see, okay, so this Hamiltonian is PT-symmetric because if you apply T operator with just complex conjugation and multiply it by P from the left, it is the same as multiplied H from the left and P on the right, and T acts on the right. And plus in the yeah, and plus in the unbroken phase, so unbroken phase corresponds to the case when all eigenvalues of this Hamiltonian, so both of them, are real, and simultaneous eigenstates of this of H and PT are these two. So essentially, when you apply P and T, so you would swap these two, and when you complex conjugate, they return backwards. And in the unbroken phase, it is so basically you can see that this Hamiltonian must be PT-symmetric. This is first, and second. So this eigenfunctions, they like eigenvectors, they are both eigenstates of H and PT. So okay. Then, PT-symmetric quantum state discrimination for two states was developed in this paper. Nevertheless, probability of successful post-selection was not identified there because general operation, if you apply e to negative IHT, so this is not non-unitary, and as a result, probability of success is less than 1 in the general case. So we extend this framework for 3 states and derive exact probabilities of maximum success probabilities for both 2 and 3 states. And unlike previous studies, our results allow for quantitative performance evaluation of arbitrary PT-symmetric scheme acting on three states. Because, like in previous studies, researchers just implemented PT-symmetric transformation by numerically. And unlike that, we actually derive exact results. We derive exact result in probability of successful post selection. Let's go to our scheme. So we go backwards. So first you can it's just easier to just visualize it, I think, backwards. So let's start with step number 3, which is the last step. So if you have two vectors in such positions, in such initial position, chi1, chi2, and the third vector in such position, then you can observe that PT-symmetric transformation maps them to orthogonal orthogonal states, because if you transform this by PT symmetry, you will get up to a normalization coefficient the same state, like 1 plus minus I. And as a result, this cosine squared is always 0 regardless of the value of alpha, because this is just a normalization coefficient. However, this alpha can be used to rotate the third state. So essentially, these two states remain orthogonal to each other, but alpha parameter can be used to adjust the angle to the third state, or like overlap of the third state with the reference vectors. Like, for example, this. So essentially, this vector and this vector remain orthogonal, but the third vector you can rotate using this alpha parameter. So okay, so mm, yeah, and essentially, first two steps are you first two steps are designed to convert arbitrary three states to such initial position for step number 3. So basically, how is it done? You take two of three states which can be completely arbitrary, and you put them on this yeah, basically on this phase, like plus or minus I. So basically you are putting it here, right? And after that, you are applying the first PT-symmetric transformation, which maps them to the north and south poles. And after they are on the north and south poles, you can rotate the third state to such a position, so that basically it gets this phase I that you actually need. Uh, so right, so essentially, yeah, that's all. So first you just take first two states, adjust them here. After that you rotate them, and as a result you're getting this, and then you apply the second PT-symmetric transformation. So that's it. That's all scheme. There is a lot of trigonometrical things, and there is a lot of trigonometry, but essentially idea is quite simple. So you just rotate this, rotate this. After that, rotate again, but rotate by a unitary operation. So this one is PT-symmetric rotation, so non-unitary. But this one is unitary. And then you apply one more PT-symmetric transformation to adjust the third angle. Okay, so after that, the question is, since such transformation is not unitary, this must be implemented as probabilistic quantum gate, and which is embedded into larger Hermitian system. So basically, to make sure that such transformation is possible, you need to maintain all eigenvalues of this zeta operator real. And to do that, you need to choose this and not value accordingly. So in such a way that it's large enough to maintain all its eigenvalues real. So unlike previous work, we analytically found this value of n naught, because like in previous work, researchers just found them numerically. And by analytically founding this n naught, we can just compute maximum post-selection probability exactly. So because minimum value of n naught corresponds to maximum value of decisive probability because it is in denominator, right? So as an example of, okay, so first let's describe the first PT-symmetric transformation. So basically you take two of the states. So you basically take two of the states and you put them on north and south, right? So to do that, we apply, so first we found not numerically, but analytically. Analytically, we found that this transformation is only possible if such condition is met. And the state in the middle actually, so basically, if you consider the state in the middle to be like along the same, okay, parallel meridian, I don't remember, yeah, so by basically along the same phase, right? Then this is actually a partial case of n equals 2 quantum state, unambiguous quantum state discrimination, because you can, because in this case, yeah, and post-selection probability is different for whether sigma is greater than 0 or less than 0, because depending what is larger, tangent or cotangent of sigma over 2. Yeah, and here the third state may be anywhere. I'm just telling about just a partial case when the third state is exactly somewhere in between them. And actually you can see that on the edges corresponding to these orthogonal states, so basically on plus minus sigma, you can see that this actually equivalent for conventional unambiguous quantum state discrimination. So this provides an alternative derivation of the same fact, but yeah, but also we extend this for the case of three states. And basically here are some illustrations. So if you have two states which you make orthogonal, and third state is right in between them, you can see that on the edges it's 0 or 1, right? So 1, 0 or 1. And you can see that the states that are more like closer to each other, they have lower probability of decisive outcome because they are less distinguishable. And similarly, you can see here that if you have two states, if you make them orthogonal, and the third state essentially is somewhere like a phase, then for the case of like for the case of smaller sigma, you can see sharper graphs because essentially you're stretching the block sphere like stronger, and as a result you can see more distorted geometry like this. Then after you apply the second PT-symmetric transformation, so essentially this step, right? So this step corresponding to this transformation, then you get these results. So minimum value that is required for performing such an evolution is given here, and success probability after second PT-symmetric transformation is given by these two formulas depending on the value of alpha. And you can see here what happens as alpha goes higher, as alpha approaches pi over 2. You can see that basically cosine squared just flattens out, it becomes almost 1. You can see this. And on the other hand, you can see that this gain in state distinguishability is counterbalanced uh, by decisive outcome. So probability of decisive outcome goes down at the same time as probability of at the same time as cosine squared goes to 1 when alpha goes to plus minus 2. So essentially just corresponding to this. So okay, now mm, you can actually compare this, and you can see that essentially when you just compare this, so if you just take into account both post-selection probability and cosine, you can see that this scheme doesn't lead to better state distinguishability because here like all values of rho are scaled by the same factor, and here is they are essentially the same. And nevertheless, and I think that's the main point of our paper, is that uh, like despite the fact that this transformation doesn't improve the state distinguishability when you take into account probability of decisive outcome, then but still the scheme offers substantial technical advantages. And first we implement this on IBM quantum experience, and first we perform PT-symmetric so we compute the metrics corresponding to PT-symmetric evolution by the dilation method numerically, and after that we decompose that into elementary operations and C knots, into elementary U3 gates and C knots. So U3 gates is essentially just a unitary rotation, just an arbitrary unitary rotation applied on a qubit, and this is C naught. And there is a post selection, and there is a resulting state. So essentially, this is in a result of our implementation for sigma equals 6/5 on all available at the time quantum processors on IBM Quantum Experience. So then this is the result of implementation for when you vary the phase. So this and this, and then this is the results of implementation when you have like states closer to each other. So basically, it has lower decisiveness, and same thing for same thing for the case when you vary the phase. And you can see sharper curves again because in this case the states are closer to each other, and as a result you are stretching the Bloch sphere stronger. It's the same thing here. Now let's take a look what happens when you approach exceptional points. So in this case you have exceptional, so you have alpha pi over 2 minus 1. So you have this, and then if you do it like this, you see this, right? So as you approach exceptional point, cosine essentially flattens out. You see, right? So like this, right? You see that, right? Okay, so essentially when you, and okay, so this, and essentially here what you can see is that this for quantum processors, simulator MPS, simulator extended stabilizer, IBM-Q, QSM simulator, simulated state vector, they actually have a better agreement with our theoretical computations. So here we just run only for them for attack on three-state protocol. And in this case, here is a nice illustration. The fact that when you post-selection success probability of different states, it differs. So essentially, this one is like when it corresponds to like this or this, right? So first, when you make cosine squared 1, cosine squared 0, so you take two of the states, you make them orthogonal, and after that, but what do you see? That the state in the middle actually has decisive probability equals 1, while this one sometimes like succeeds with probability of 50%, and this one as well. So you can read in more details in our paper that essentially this, as a result, uh, it leads to exactly the same error rate as conventional minimum error and maximum mutual information strategies. So essentially, it doesn't decrease the error rate for quantum key distribution. Nevertheless, it gives technical advantage for post-selected metrology. So basically, in Hermitian metrology, you have quantum Fisher information, and it comes at the price of preparation measurement, preparation cost, and measurement cost. While in PT-symmetric metrology, you have some probability of post-selection, And also you have the post-selection cost, processing cost, and also what is important, you perform measurement not all the time. Sometimes you skip some measurements. So if some measurements fail, you just skip them. You don't measure them. And as it was shown in this paper, basically post-selected metrology actually enhances information cost rate when you can neglect when basically cost of measurement is much greater than everything else. Because in this case, so that's and what we've shown is that we can actually relax this condition because experimentally this condition might be too demanding when cost of measurement is very high. Like maybe, so basically that this advanced, so PT-symmetric sensors are advantageous to emission ones even under relaxed conditions. So when this is not much greater. And here are like exact computations of like using our formulas. Here you can see quantum Fisher information, and in post-selected space it is much higher for the case of PT symmetry. Nevertheless, when you multiply it by probability of decisive outcome, it's not larger than in the Hermitian case. So you can see this. But as we will show further, information cost rate is greater than this. So you will see it in the next page. So what you can see is that you can just compare this and this, and since we derived exact probabilities of successful post-selection, we can just compute when PT-symmetric sensor has higher information cost rate than Hermitian sensor. And this condition just relaxes to this. And what you can see here is that near to the exceptional point, so close to the exceptional point, like this one, where quantum Fisher information is high and like essentially it corresponds to this point when cosine squared suddenly jumps from close to 0 to 1. So essentially in this region of space, um, you can see that in this region of space this is almost 0. This coefficient is almost 0. So this coefficient is almost 0. And this coefficient is approximately 1. So you can see it here. So basically, if your PT-symmetric sensor operates sufficiently close to the exceptional point, then this condition can be relaxed to a much less restrictive of cost of measurement greater than, if cost of measurement is greater than post-selection cost, then essentially PT-symmetric sensor outperform its Hermitian counterparts. And as we show in our paper, I mean, it's as we discuss in our paper, in practical schemes, this post-selection cost can be actually really small, and thus this shows that PT-symmetric sensors that PT-symmetric sensors outperform their Hermitian counterparts in wider range than it was thought before. So like this is reduced to this. Okay, so now similarly we can apply this for the depth limited Grover search algorithm. So essentially, since Grover's search algorithm effectively operates in two-dimensional space, then our results for which we derived for qubit are directly applicable here. So as you can see, so this is the state of Grover's. This is the Grover state after k applications of Oracle, right? And you can yes, and for example, what you can do, you can like in practice sometimes it's advantageous to not complete the whole cycle of Grover search. For example, you can stop right like in the middle. If you stop right in the middle of the complete cycle, Grover cycle, then probability of success is exactly 50%. Uh, but you use half of Oracle calls that is needed to you to run the whole Grover search. So this, and so as a result, the number of Oracle calls is exactly the same as in the original Grover search algorithm, but the depth is reduced 2 times. However, at the same time, what does it do? It doubles the qubit readout cost because on average you need to read the outputs twice, like because success probability is one half, and effectively there is a punctuated version of Grover search algorithm uh, which uh, which is actually advantageous to stop the search of Grover search before reaching the final point, because you can essentially just compute average number of Oracle calls needed to find the solution, and it turns out that its optimal value is not at the end; it's actually here. It's at this value of Oracle calls, and essentially reducing the depth lowers the average Oracle count. So so basically you this point is not very visible here, but this point is smaller than this point. But all this comes at the cost of sometimes failing, which increases the number of final qubit measurements. So essentially, you need to read the output more than once. And one more thing is that in like real life conditions, qubit readout cost actually matters. Like on current quantum hardware, readout errors can be as high as 10%. Readout time is also large, and thus reusing qubit readouts is critical for improving the reliability of your quantum algorithms. And plus, it may be inevitable that you need to operate at some limited depth of your quantum search because there is a max depth parameter by NIST. So quantum circuits implementing the Grover's algorithm, they have technical depth constraints. And this is especially relevant in the context of cryptographic applications. So, and how our scheme can be helpful in this context. So, if you apply PT-symmetric transformation to the Grover state before the completing the full cycle, then probability of success is this one, right? Uh, if you apply at this point PT-symmetric transformation, if your post-selection is successful in the alpha limit to pi over 2, then success probability goes to 1. You are paying the price for this, that probability of successful post-selection like goes to this, right? And as a result, total success probability it remains unchanged, and thus you need to apply the same number of Oracle calls as in the original punctuated version of Grover search. Nevertheless, it gives you an advantage in qubit readout cost because in post-selected readout you are reading all working qubits just once, only when Anzilla is measured 0. So essentially corresponding to this case. Only when Anzilla is measured to 0, then only then your PT-symmetric transformation is successful. But if it's 1, you certainly know that you failed in this case. So but if you failed, you don't reinforce. So you reinforce success. You don't reinforce defeat. So you know that when a solution is not successfully found, then you do not waste valuable resources, which is qubit readout cost, on this case. So like you skip all these measurements, and let's say, and as a result total readouts in PT-symmetric scheme is just this. So you need to read a single ancilla, possibly several times, because decisiveness is so basically because decisiveness may be less than one, and you are reading all working qubits only once, only when ancilla post selection is successful. And essentially, if you compare it to the remission case, in the remission case, you would need to read all n qubits one over this. And essentially, in comparison to the remission case, in the limit of many qubits, this is always less than zero. And several examples of this. So if you have like optimal depth circuit, which is 1.18, this is reduced to n, and if you have half depth, then this is reduced to also to n, right? So no matter, like regardless of the depth of your circuit, it's always n, right? Okay, so and essentially, if you are having shallow depth searches, you may have even to read this like many times, like 10 times or 5 times. But regardless of the depth of your circuit, our scheme enables you to read only in the case when you certainly know that solution is there. If solution is not there, you are skipping. You are not reading that. Okay, so conclusions. So first of all, PT-symmetric. I think the main point of our paper is that PT-symmetric scheme systems not only exhibit some interesting behavior or some unusual properties, but also they can be advantageous on the over Hermitian systems on the tasks of practical interest. And by developing a new algorithm for mapping three arbitrary qubit states and developing exact expressions for post-selector probabilities, this enables us to uh, rigorously evaluate the performance of such systems. And also we verified our computations on IBM quantum experience. And thus, like two main conclusions is that PT-symmetric metrology achieves higher information cost rate in comparison to Hermitian systems and it can be under relaxed resource constraints. So basically, just when cost of measurement is greater than cost of post-selection, and thus our results are showing that such sensors can be advantageous in wider range of conditions that considered before, but also in punctuated and depth-limited Grover search, you need to read all working qubits essentially once, and this is for arbitrary depth. Which may have applications for like for cryptography and for max depth parameter and all that. Number of oracle calls remains the same as in the punctuated version of Grover search, right? So our next step would be to apply these results to quantum sensing and protocol design. So I really appreciate your attention, and thank you very much for your attention. I would welcome all your questions, like any type of discussions, suggestions. So please contact me on these two emails. And thank you for your attention again, and have a great day.